The topic of this lecture is Important Theorem, Part 3 of Complex Analysis. We'll cover these points in this lecture: Cauchy inequality, Liouville theorem, and theorem derivative of analytic function. So let us see the first theorem, that is Cauchy inequality. The statement says that if fz is analytic inside C, where C is a circle, z minus modulus z minus z naught is equal to r, and if modulus of fz is less than equal to m on C, then modulus of nth derivative of f at z naught is less than equal to m times factorial n divided by r to the power n. So let us see the proof. So here C is given as a circle, mod z minus z naught is equal to r. So this implies z is equal to z naught plus r e to the power I theta 0 less than theta less than 2 pi. This implies dz is equal to I r e to the power I theta d theta, where theta lies between this interval. Now we know that nth derivative of f at z naught is given by factorial n divided by 2 pi I integration over c of fz upon z minus z naught to the power n plus 1. Thus, we have modulus of nth derivative of f at z naught. This will be less because of this. It will be less than equal to factorial n upon modulus 2 pi I integration over c of modulus fz modulus dz divided by z minus z naught to the power n plus 1. From this we obtain that this expression is less than equal to factorial n upon 2 pi m upon r to the power n plus 1, because z minus z naught is equal to r using this. 0 to integration 0 to 2 pi r times modulus I minus I into e to the power I theta d theta. From this we get factorial n upon 2 pi m times m upon r to the power n plus 1 into 2 pi r. And from this we get final result as this expression is less than equal to factorial n into m divided by r to the power n. So by this way, this Cauchy inequality is proved. Now let us see the next theorem, that is the Liouville theorem. It says that if a function fz is analytic for all finite values of z and is bounded, then fz is constant. So let us see the proof. Let z naught be any arbitrary point. So then we know from the Cauchy inequality, we have seen the last slide, that modulus of nth power of f at z naught is less than equal to factorial n times m divided by r to the power n. Now here in this inequality we take n is equal to 1 and let take r tends to infinity. Then we get modulus of first derivative of f at z naught is equal to 0. This gives that derivative of f at z naught is equal to 0. And as z naught is arbitrary, this implies that fz is constant for all finite values of z. Now let us see the next theorem. It says that if a function f is analytic in a given at a given point, then its derivative of all order are analytic there too. So let us see the proof. Let f is analytic at a point z naught, then there exists a neighborhood modulus z minus z naught less than epsilon of z naught throughout which f is analytic. Therefore, there exists a positively oriented circle C naught centered at z naught and with radius epsilon by 2 such that f is analytic inside and on C naught. So just see this figure. Accordingly, we have assumed the circle C naught with center z naught and radius epsilon by 2. Then we have second derivative of f at z is equal to 1 upon pi I integration over C naught fs ds divided by s minus z cube at each point. The value of this is given by this integration and this exists at each point z interior to C naught. This implies that f double dash z exists throughout the neighborhood z minus z naught less than epsilon by 2. that is f double dash z exists in this neighborhood. But this implies that fz is analytic at z naught. So if f is analytic, we have proved that fz is analytic. Now fz is analytic. Now applying the same argument to the analytic function f dash, we conclude that the derivative f double dash is analytic. Therefore, by induction, each derivative fn of f is analytic. So thank you very much. You can find the link of this PPT in the description box. Thank you.